Good afternoon, scholars. This is Mr. Lowe. I am audio recording the following lesson on section 6.4, which are inverse functions. So for this, we are going to learn how to write an inverse function, how to determine whether the inverse is a function based off of a graph, and finally, how to verify if two equations are inverses of each other. Again, this aligns with section 6.4 in your notes packet. So, to understand the concept of an inverse, we have to know what an inverse is. Simply put, an inverse means the opposite. You're doing the opposite of what was in the original function. So, one thing you have to know is notation. So, the original function will have the original notation for a function. So that's f of x. Now, f could be G, H, whatever letter of the alphabet, but that's the original notation. Inverse notation looks like f to the -1 power, but that's not how you say it. It's f inverse. So it's not f to the -1, it's f inverse. So the original is f of x, the inverse is f inverse of x. Now, to understand fully what an inverse does, you have to know your opposites. So if you look in this box that is on the left-hand side of your screen, it gives you what some of the primary opposites are. So for example, if you have adding in a problem, you would cancel it out with subtraction. If you have subtraction, you cancel it out with addition. Multiplication, you get rid of it by dividing. Dividing, you get rid of it by multiplying. If you have something raised to the second power, so for instance, if you have x squared equals y, to get x by itself, you would take the square root of both sides. If you have something raised to the third power, it means the exact same thing. It has the radical side sign with a 3 outside of it. And that's how you would get rid of a cube. So that's how you would take care of the powers. If you started with the roots, then the opposite is to take that power. For example, if you have the square root of x equals y, and you want to get rid of the square root, you raise both sides to the second power. A square and a square root are opposites. They drop out. So you get x equals y squared in this case. Same rule applies if you are dealing with a cube root. If you want to get rid of a cube root, then you raise it to the third power. Raise both sides to the third power. Again, a cube and a cube root are opposites of each other. They drop out. So when you're solving an inverse function, it is important that you know what the opposites are. It's important that you know opposites. So with that being said, we are going to look at how to write the inverse of a function. So this will take us into our notes packet. We've already done page 9 in the notes packet, so we're going to look at examples that are on page 10 of this notes packet. If you were absent on last week Friday, please make sure you get the notes that you missed from last week Friday. Let's take a look. So to write the inverse of a function, there are 4 steps. First step, replace f of x with y if your problem is in function notation. So that's a simple replacement. Step 2, switch your x and y variables. It means exactly what it sounds. Switch the variables. Step 3, solve the equation for y. Step 3, is the step that probably takes the longest because that's where all of your algebra is being done. And then finally, step 4, replace y with f inverse of x. So you're putting it back into inverse notation. So with that being said, let's go on and do a couple of examples. Now, examples 2, 3, and 4 were already done in the notes from last week, Friday. So I'll quickly provide what those answers were so that we're all on the same page. So for example 2, the inverse function was x minus 3 divided by 5. For example 3, the inverse function was g inverse of x equal to x squared minus 1 divided by 3. Last but not least, the example 4, h inverse is equal to the cube root of 4 parentheses x plus 2. Could have left it that way, or you could have given it as the cube root of 4x plus 8. So if you notice, no difference in between the two. One stayed the way it is, and one is the simplified version of it. So no difference one way or the other. So that's examples 2, 3, and 4. We're now going to do 3 more examples together just to make sure that we're on the same page. Example 5. So example 5, find the inverse of each function. Now, for those of you who do work ahead, I will put what the answer should be if we do it correctly. So if we do in fact do this problem correctly, you should have g inverse of x equal to the square root of x minus 1 over 4. So that's what the answer should be if we solve this problem out correctly. So now let's go ahead and solve it. First step is to take g of x out and replace it with y. Replacement step. Second step, take y, take x, and literally switch places. You're literally taking the variables and switching them. So just like that, steps 1 and 2 are done. Now we solve the equation for y. So you want to get y completely by itself. So you have a positive 1 that has to go, a 4 that has to go, and a squared that has to go. So we're going to eliminate all 3. Subtract 1 on both sides. X minus 1 equals 4y squared. Then divide both sides by 4. X minus 1 divided by 4 equals y squared. Finally, to get rid of y squared, you have to take the square root of both sides. So the left-hand side, there's nothing that we can accomplish there. Rewrite it. On the right-hand side, a square and a square root are opposites, so they drop out, and you're left with y. So that completes step 3. Remember, step 3 is the longest step because that's where all the algebra is. Step 4, the last step, is simply putting it in the correct notation. So take y out of the problem and replace it with the inverse notation. Replace it with the inverse notation. And that's your final answer. So for an inverse, again, you're literally doing the opposite of every operation that's there to rewrite a brand new equation. So with that, let's do example 6. So example 6, let me first provide the answer that you should get if you do it correctly. For those of you who have worked ahead, that would be h inverse of x equals x plus 6 divided by 5. So that's the answer that we should have if we do this correctly. So again, let's go ahead and solve this out. H of x out, replace it with y. X and y, switch it. Now we can get to work. To get y by itself, add 6 to both sides. And then divide both sides by 5. That's x plus 6 over 5 equals y. Y is now by itself. We've finished solving out the equation. Now we put it in the right notation, cross out the y, and replace it with h inverse of x. And that takes care of that. So last but not least, let's take a look at example number 7. So example 7, let me throw the answer up here in the event that you've already started the problem. So the answer for this problem can be given in 2 ways. So f inverse of x is equal to x plus 4, the quantity squared. Or if you did simplify it out, x squared plus 8x plus 16. So depending on what route you took. So now let's go ahead and solve it out. Replace f of x with y. And then switch the variables. Here's one important thing to keep in mind. That square root is over the y variable. It's not over the 4, it's just over the y. So keep that in mind as you now start solving. So to get y by itself, add 4 to both sides. So that's x plus 4 equals the square root of y. And again, going back to what we did earlier, in order to get rid of a square root, you have to raise both sides to the second power. So a square and a square root are opposites, so you're left with y. Get rid of the answer momentarily. And x plus 4 squared stays x plus 4 squared. We finished rewriting it, so now replace y with function the inverse notation. So you can leave this as your final answer, but as I mentioned earlier, you can simplify out x plus 4 squared. X plus 4 squared is simply writing it twice and performing FOIL to the problem, distributive property. And there you go. So again, you don't have to take it that far, but if you are going to take it that far, do make sure that you simplify it correctly. So that completes part 1 of the objectives for this section, learning how to rewrite a function into its inverse. So this completes the first objective. Now we'll move on to objective number 2. Objective number 2 is how to verify an inverse. Verifying inverses occur 2 ways, based off of a graph and based off of 2 functions. So we're first going to verify it off of a graph. So in the first semester, if you were given a graph, you could tell whether or not it was a function by doing what's called the vertical line test. The vertical line test was done to prove whether or not a graph was a function. So for each graph, you literally drew a vertical line through it. You literally drew a vertical line through them. In order for it to be a function, it can only touch the graph one time. It can only touch whatever graph was there once. So in the case of example 1, it only touches it once, so the original function is a function. In example 2, it touches it twice, so that fails, it's not a function. Example 3, it only touches it once, so it is a function. Now, since we're dealing with opposites, the opposite of vertical is horizontal. So to see if an inverse is a function, we do the horizontal line test. We do a horizontal line test. So it means exactly what it sounds. We're going to draw a horizontal line, and it can only touch that graph one time. So if you look at example 1, if you draw a horizontal line, it touches that graph 2 times. That's a fail. It can't touch it more than once. So the inverse is no. So I want you to notice that the original works, but the inverse does not. It will happen like that sometimes. It can happen like that sometimes. Let's do example 2. Draw your horizontal line. Again, it touched the graph twice. Can't do that. That's a no. The original wasn't a function, and neither was its inverse. It can happen like that. And example 3, draw your horizontal line. And sure enough, it only touches it once. So it is a function. So just know that sometimes it can work both times. Sometimes both of them could fail. And sometimes one could pass and one could fail. So don't assume, do the work. Don't assume, do the work. But just like that, that completes objective number 2. Verifying whether something is an inverse using a graph. So the last thing that we're going to look at is how do you verify an inverse algebraically? So algebraically means we use function composition. We use function composition. So just to remind you what function composition is, that's plugging one function into another. One function into another. Remember, that notation is f of g of x. When you have one function plugged into another, or f with the open circle in the other function after it. That's function composition. In another video, I will review the 6 types of operations that go with a function: adding, subtracting, multiplying, dividing, composition, and the inverse. But to verify whether 2 functions are inverses, you're going to take one function, plug it into another, and you must get back an answer of x. Period. End of story. You must get back an answer of just x. Not x plus 1, not 2x, x. That's it. And, this is important, I should be able to do it the other way around and it still works. Take one, plug it into another, get back an answer of x, switch the functions around and do it again, and still get back an answer of x. Both of them must work. So, key thing here, you must do both parts of the problem, and both of them must give you an answer of x. If you get any other answer, the functions are not inverses, point blank and period. So, it's not a hard problem. It is a little bit of algebraic work. So, I'll tell you that in advance. So, let's start with example number 4. So, example 4, they're giving us two functions, and we need to verify that they are inverses of each other. We need to verify that they're inverses of each other. So, step 1, find f of g of x. So, the f function is x squared plus 3. The g function is the square root of x minus 3. So, we're going to take the square root of x minus 3, plug it in for x. Take this function, plug it into the other. So that gives you the square root of x minus 3 raised to the second power plus 3. So now think about your opposites. A square and a square root are opposites of each other. They cancel out. So that gives you x minus 3 plus 3. Combining like terms, negative 3 plus 3 is 0. So that's x. That checks out. So step 1 checks out. If step 1 failed, then we wouldn't have to do step 2. If step 1 failed, we wouldn't have to do step 2. But since step 1 didn't fail, we're doing step number 2. Now we do it the other way around. G of f of x. So G is the square root of x minus 3. F is x squared plus 3. Take the f function, plug it for G. So that sets itself up as the square root of x squared plus 3 minus 3. Again, we have some simplifying. 3 minus 3 is 0, so that gives you the square root of x squared. And the square root of x squared is x. Boom, checks out. It checks out. So since both answers were x, the answer is yes. The answer is yes. As I mentioned, it's not so much that it's a hard problem, but it is one that is algebraic intensive. You're going to have to put in some work. So let's do example 5. Hopefully you're ready. Let's get to it. Verify that f of x and g of x are inverses. So the same rules apply. F of g of x goes first. So the f function is 2x minus 1. G function is x plus 1 over 2. Don't get afraid of the fraction. It is what it is. Take the function, plug it in for x. That gives you 2 times x plus 1 divided by 2 minus 1. Now, to make things a little bit easier, since x plus 1 over 2 is a fraction, we're going to make this 2, put it over 1. Now, if you remember back from middle school, maybe in Algebra 1, you can cross-cancel two numbers if they are the same. Notice that this 2 and this 2, they can cross-cancel. They are diagonal to each other, and they divide out. So cross cancel those out. That gives you x plus 1 divided by 1. And x plus 1 divided by 1 is x plus 1. And look at that. 1 minus 1 is 0. X. Checks. Turn around and do it the other way around. So if it works the other way, then we are 100% good to go. So g is the x plus 1 over 2 function. F is 2x minus 1. Take 2x minus 1 and plug it in for x. So that would give you 2x minus 1 plus 1 divided by 2. Negative 1 plus 1 is 0. So 2x over 2. 2 divided by 2 is 1. That gives you x, and that checks. That checks out. Both times it checked out, so your answer is yes. Now, you might be wondering, is it ever a time when the answer will be no? Again, if you don't get the answer of x 2 times, then the answer is no. But for the majority of the time, anytime your directions are telling you to verify, they're asking you to verify, it's a pretty safe bet that it works. You just have to show that it works. It's a pretty safe bet that it works. You just have to show that it works. So let's do one more final example. So we have 2 functions given there. Go right ahead and get to it. F of g of x. The f function is 2 over 5x plus 4. The g function is 5 over 2x minus 10. Take g, plug it into f. So that's your first step. 2 over 5 times 5 over 2x minus 10 plus 4. So distributive property comes into play here. 2 times 5 is 10. 5 times 2 is 10. So 10 divided by 10 is 1. So that's x. 2/5 times 10 is 4. And negative 4 plus 4 is 0. X checks out. Now let's do it the other way around. G of f of x. G function is 5 over 2x minus 10. F function is 2 over 5x plus 4. Plug in. Plug it in, the same rules apply. 5 times 2 is 10. 2 times 5 is 10. 10 divided by 10 is 1. 5 over 2 times 4 gives you a positive 10. And 10 minus 10 is 0. So you get x. Both answers work, so the answer is yes. The answer is most definitely yes. So again, to verify it algebraically, you're doing function composition. So to recap, we started by just writing the inverse of a function, and then we verified it both using a graph and algebraic using compositions. So use this video, rewind it, fast forward as much as you need to get the help that you need. If you are continuing to struggle, come on in, get the extra help, come to tutoring. I'll see you later.